Hello friend, today we are going to learn the classical mechanics and point is the derivation of Lagrange's equation from Hamilton principle. You know the principle, Hamilton principle, the fundamental problem of calculus of variation is easily generalized to the case where f is the function of many independent variables, that is yi, and their derivative yi. Of course, all these quantity are considered as a function of parametric variable x. Then a variation of the integral j is given by del j, means first write the proof and then write f is function of many independent variable. Many independent variable yi and their derivative yi dot, then variation of the integral, then a variation of the integral j, that is del j is equal to del integral 1 to 2 f of y1 of x, y2 of x, del dash y1 dash of x, y2 dash of x, dash 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 x dx, and is obtained as a before by considering j is a function of parameter alpha. Is obtained, this is equation 1, is obtained as before by considering j as function of parameter alpha that labels a possible set of curve y1 of x alpha. Then thus we may introduce alpha by setting y1 of x alpha is equal to y1 of x comma 0 plus alpha into eta 1 of x, and y2 of x alpha is equal to y2 of x 0 plus alpha into eta of x. This is equation 2. Here y1 of here y1 of x comma 0 and y2 of x comma 0 etc are the solution of extreme problem, and eta 1 eta 2 etc are independent independent function of x. And independent function of x that vanish at the end point, at the end point and are continuous through the second derivative, and continuous through second derivative, but otherwise are the completely arbitrary. The calculation proceeds as before. The variation of j is given in term of del j upon del alpha into d alpha is equal to integration 1 to 2 summation I into bracket del f upon del yi into del yi upon del alpha d alpha plus del f upon del yi dot into del yi dot upon del alpha into d alpha into dx. This is equation 3. Again we integrate by part, and integration involved in the second sum of the equation 3. We get the integration 1 to 2 del f upon del y I dot into del 2 y I upon del alpha del x dx is equal to del f upon del y I dot into del y I dot upon del alpha taking point 1 to 2 minus 1 to 2 del yi upon del alpha derivative of x df upon dyi dot dx. Means integration by parts we use in the second term of the above equation, means equation 3. Then here the first term vanished because all the curve passing through the fixed end point, and substituting the equation 3 in del j, then del j become del j is equal to integration 1 to 2 summation I into del f upon del yi minus the derivative of x del f upon del yi dot into del yi into dx, where analogy with the equation del y upon del alpha at 0, d alpha is equivalent to del y, and the variation del yi is equal to del y upon del alpha at 0 d alpha. Since the this y independent variable and variation of del y are independent, and then in this example nix will be independent with each other. Hence, by the obvious extension of the fundamental lemma, the condition of del ij means here del j is 0 requires the coefficient of the del y separately vanish. Then del f upon del yi minus d upon dx into del f upon del y dot is equal to 0, and here I is equal to 1 to n, and this is equation number 5. The equation 5 represents the appropriate generalization of the Lagrange's equation and to several variables and are known the Euler-Lagrange's differential equation, and this equation is known as Euler's Lagrange's differential equation. Their solution represent the curve for which variation of integral of the equation number 1 vanish, and further generalization of the fundamental variation problem are easily possible. Thus, we can take f as a function of higher derivative of y double dot y3 dot etc, and leading to the equation different form of the equation number 5, and we can extend it to the cases where there are several parameter xj and integral is the multiple, with the f also involving as a variable derivative of yi with respect to each of the parameter xj. And finally, it is possible to consider the variation in which the endpoints are not held fixed. For present purpose, we have derived here suffix for integral in the Hamiltonian principle, and Hamiltonian principle is given as I is equal to integral of 1 to 2 L of qi dot t dt. This is equation number 6. Has the just form of the stipulated in equation 1 with the transformation x transfer to t, yi transfer to qi, and then f of yi dot x are transferred to L qi dot t, and in deriving the equation 5, this 5, we assume that the yi variable are independent. This yi is an independent variable, and the corresponding condition in the connection with Hamiltonian principle is that the generalized coordinate qi and qi be independent variable and which requires that constant be holonomic. The Euler-Lagrange equation correspond to integral I then become the Lagrange equation of the motion, and Lagrange equation of the motion is given Lagrange motion or Lagrange equation of the motion is given by d dt del L upon del Q I dot minus del L upon del Qi is equal to 0 where I is equal to 1 to I. And we have accomplished our original aim to show that the Lagrange equation follows from the Hamiltonian equation for monogenic system with holonomic constant.